We're now going to apply the ideas of electric field and electric potential to a specific example, and that is parallel plates. So first let's draw what the electric field looks like between two parallel plates. And let's consider that these two plates have the same amount of charge, the same size of charge, and it's evenly distributed, so it's uniformly distributed. So they're the same size of charge, oppositely charged, one's positive and one's negative, and those charges are evenly distributed. So you might want to just take a moment and have a think about what a positive charge would do if it were placed somewhere in that field. And of course it's going to be repelled from that, so if it's right near that plate there, it will be repelled from it. It will be heading down the way, there we go, down the way this way. It's not going to go to the right or the left, or the right or the left, because if it was heading this way it would be repelled by the positive charges further over here, and so on. So if you look at the electric field inside, directly in the middle between two parallel plates, you'll find that it's a uniform field, so those field lines should be evenly spaced, and they're all heading directly perpendicular to the plane of the plate. Of course at the ends you have a little bit of bowing, goes out a little bit, because you don't have that direct attraction and repulsion directly between the plates. But in the center there is a uniform field. It's actually the really special thing about parallel plates is that this electric field, which is between the two parallel plates, such as this here, is uniform. And if we have, I'll just write this up here, if we have the definition of the electric field, which is force per unit charge, if the charge is unchanged and our electric field is uniform, which means it isn't changing anywhere in that space, then the force on that charge is going to be the same no matter where you are. So let's have a look at this example. We've got here a uniform electric field of 275 newtons per coulomb between two parallel plates here, a charge of positive 12 microcoulombs, and it has a mass of 0.25 grams. So the first question is, what is the electric force acting on the charge? And so if we look at our working out here, we know that the force, taking that equation that we had up the top there, by definition is the electric field times the charge, and we go ahead and substitute those values in. It's 275 times 12 microcoulombs, which is 10 to the minus 6 coulombs, and that gives you an answer of 3.3 by 10 to the minus 3 newtons. 3.3 by 10 to the minus 3 newtons. Too easy. Alright, let's have a look at part B. What is the weight of the charge? Well, the weight of the charge has got nothing to do with the electric field, but we do have its mass. So its mass is here. You have to remember that the mass should actually be in kilograms, so it's 0.25 by 10 to the minus 3 kilograms, which is the 0.25 grams. The weight is the weight force, is mass times acceleration due to gravity, which we can just, let's just use it as 10 for now. And so what we end up with is 2.5 by 10 to the minus 3 newtons. Alright, so our force on that charge is going to be going upwards in this graph over here, but our weight force will be going down the way. So let's just keep that in mind as we move on to the next part of the question. Okay, so here we are again. It's exactly the same question, 275 newtons per coulomb as the strength of the field, positive 12 microcoulombs, and a mass of 0.25 grams. So the question this time is, what is the acceleration of the charge? Well, we know that the force upwards was, what was it, 3.3, I hope that's right, by 10 to the minus 3 newtons. The force downwards, due to gravity, was 2.5 by 10 to the minus 3 newtons. So we've got one force going up, one force going down, and so the net force will be going upwards. So that's the net force there, and it will be the difference between the two. So the net force is the difference between those two. So it's the 3.3 by 10 to the minus 3 minus 2.5 by 10 to the minus 3, which gives us 8 by 10 to the minus 4 newtons, and that's going upwards. If we have the mass, if we have the force and the mass, we can find the acceleration. So we know that F equals ma, which means we rearrange that. The net force divided by the mass is 8 by 10 to the minus 4 divided by our mass, which is the 0.25 grams, so it's 0.25 by 10 to the minus 3, which gives us an acceleration of 3.2 meters per second squared in the upwards direction. So in this example, we're going to be talking about potential difference between the parallel plates, and we know that the potential difference between 2 points A and B, say, is just the work done per unit charge against the field moving from A to B. So we're moving a positive charge from A to B, and in that case it's going to be moving against the field there. So the first question is how much work is done in moving charge Q through the distance D, and the second question is find the potential difference across the plates. So what we're going to do is have a look at, for part A, the work is just force times distance, and we also know that the force against the field will be the electric field strength times the charge, because the electric field is defined as the force per unit charge. And we know this force doesn't change in that space because the electric field is constant throughout that space. So the force due to the electric field will be constant. So all we need to do now is substitute that force F into that equation there. So we're left with work equaling electric field strength times the charge times the distance. And that gives us the amount of work done in moving that charge through the distance D between the plates. For part B, all we need to do now is turn to the definition of potential difference. And the potential difference is the work done per unit charge. So if we then take our solution to part A and substitute it into that definition, what we get is V, the potential difference, is E Q D on Q. The charges cancel, and what we get here is the potential difference is the electric field strength times the distance between the plates. And this is a really, really useful equation, which I imagine that you'll have cause to use sometime when you're doing some problems for this. But getting to this point is actually not that much of a challenge to show that the potential difference between those two plates is related to the electric field strength and the distance between the plates.